think that's all. One more thing, the videos will be published on YouTube, on ICTP's Diploma channel. Do you agree? Yep. Okay, thank you very much.
Can you please pause it? Okay, welcome. So this is my contact info, just in case. So you can reach me by email, or you can also come by my office. My name is Putrov. Okay, so edition of Algebraic Topology. So the course is quite short, it's just 10 lectures, so it will be really some basic topics, introductory. So many of you probably will know some of the things, so you have to bear with it. I guess I should. Okay, let me start with some basic motivation. So the idea is to relate topology to some sort of algebra. So to be more specific, so for example, one of the main questions of topology is kind of classifying spaces up to a homomorphism. So you can consider topological spaces of the homomorphism. And we can try, so this is usually quite hard to understand, this space of all topological spaces divided by homomorphism. But it might be, and this is what the field of algebraic topology addresses, it might be able to construct some map from this kind of set to, for example, groups up to isomorphism. Examples of such map, which we will study, is fundamental group, homology, or homology. So what will actually happen is actually this is depends. So the result will depend not on homomorphism. So it not only on homomorphism type of topological space, but on some kind of weaker class. So when we consider spaces, the topological spaces not up to homomorphism, but what is called up to homotopy, which we will study this notion in detail. So this is compared to homomorphism, this is a weaker equivalence relation. So in particular, if two topological spaces are homomorphic, they are necessarily homotopic, but not the other way around. So it will happen that, so for example, in this example, it's like fundamental group, homology, cohomology, the resulting group will depend actually not on only on homotopy class, but it will still provide some trivial information about topology. So this is a very brief motivation. Now we will come to more concrete things. So of course, as as it usually happens in the beginning of some theory, we have to introduce some definitions. So the first lecture will contain a lot of definitions. But it's important to do this, so then one can formulate all various.
Why do we focus on proofs?
Well, this was just example of what kind of things, what kind of problems solving very for. Of course, we can consider kind of this kind of map which I wrote is kind of also some sort of constructing invariants of topological spaces, for example. But of course, we can consider invariants like in some other spaces. But the groups, as you will see, the groups will have nice properties. So the maps are not just arbitrary maps, but they have some sort of nice functionality property which we'll discuss. So let me start with the definition of homotopy. So let X and Y be topological spaces. And F and F prime continuous maps from X to Y. Then homotopy between prime is a continuous map by F from X times closed interval from 0 to 1 to Y, such that if I restrict F to a beginning of the interval, so I restrict it to X times the beginning of the interval, 0 point, it will become, so then it's become just a map from X to Y. It will be the same as F, and if I restrict F to X times the point at the end of the interval, it will become the same as F prime. So this was definition of homotopy, and then we also say that, so suppose you have a pair of continuous maps on X and Y, we say that if such F, such homotopy exists, we say that F and F prime are homotopic. And we will use a sign, the sign to say that they are homotopic, that the two functions are homotopic. Questions? So let me give you a very simple example. Let me take f and f prime, the continuous maps from an interval from 0 to 1 to R of n, where n is some integer number. Then for any pair of such maps, there is actually exists a homotopy. You can take any f and f prime, so there exists a homotopy f. So by definition, it should be a map from a. So if I consider maps from x and y, so x here is my interval, and y here is r to the n. So my f should be a map from interval times interval to Rn, and so I claim that one can choose f to be explicitly the following. So suppose I denote a variable by parameterize the first interval by s and the second interval by t, so that f s and t is let's see, it's 1 minus t. So you can visualize it as follows. So if you suppose I have R2 or a plane, so the map from interval to R2 is some path. I can assign some path. And so this is the image of my interval under map f. This is the image of the interval under map f prime. And you can see that so this function satisfies the definition of homotopy with f of 0, f of s. If I restrict t to be 0, I will get f of s, and I restrict f t to be 1, I get f prime. And this is, of course, it's easy to see this is continuous. Once f and f prime are continuous, this is the continuous. So here I understand f and f prime is valued as Rn is an affine space that can add elements as vectors. So I can understand this homotopy f, which is so it's a map from square to R2. So the image of the square will be sort of, I can visualize it in some sort of distorted square which spans between the image of f and f prime, and so that the trajectory, so if I fix one point and I fix s and start changing t, the trajectory of one point of the image will be like this. So it's another way around. It's from f to this is the homotopy from f and prime. So if I fix s, take some s here, and I start increasing t from 0 to 1, the trajectory of the image will do this. So is it clear? So far they are quite very basic, but it's important that in the beginning everything is very clear. Okay. So now we want to show the following proposition. the homotopy is an equivalence relation on the space. Well, let me just use the set of continuous maps from X to Y. So I will denote, in my lectures I will denote this set of continuous maps as map XY. So what we, so in order to show that this equivalence relation, by definition we need to check the following properties. First, we want to show that the first property, equivalence relation, is reflexivity, right? So we want to show that we have some equivalence relation where f is equivalent to itself. So it's easy to see. We can just take f in the definition before. So if x is unbound on x, is equal, and the result of the function is belongs to y, I just can take it to be constant. So this is a constant homotopy between f and itself, right? The second is symmetry. So if f is homotopic to f prime, then f prime is homotopic to f. So this is also more or less obvious. So if I take, so suppose if I realize the homotopy f, my function f is in definition realizes homotopy between f and f prime, I can realize homotopy between f prime and f by taking f prime xt to be equal to f x1 minus t. So essentially what I do, I reverse here, I do a reverse of the interval, right? So I change t to t minus t. So for example, in this example, so my trajectories will be reversed here. Okay, and second, we want to show that the equivalence relation is that we want to show is f is homotopic to g and g is homotopic to h, then we should have that f is homotopic to h. So we want to show that. So suppose the homotopy here is given by function f, and homotopy here is given by function g. Now we want to construct a homotopy between f and h, and one can explicitly present such function. So h, we need to construct the function h from x 0, 1 to y, such that h at x times 0 is f, and h at, sorry for being small, h times at x times 1 is
we can make h follow capital F at the first half interval from 0 to half, and then from half to 1 it follows g, right?
Yes, exactly. So if you want to write x explicitly, so the function of x and t, where x belongs to big X and t belongs to interval, is explicitly, indeed can explicitly written as follows. So we split our interval into 1/2 from 0 to half, and so on the first 1/2 we use a homotopy between f and g. So we can understand as a kind of if this is the interval, my interval 0 to 1. So here I first do homotopy bit from f to g and then homotopy to h. And then I can combine them. So since the original homotopy is defined, so this is from 0 to 1 and this is from 0 to 1. I can combine this interval and just carry them by half to combine these two intervals into one interval to 0, 1. And this is done by the following definition of variables. Sorry, here I need to use variables. So this concludes as a proof that this is the coordinate solution.
Continuous.
Question?
It's continuous. I was going to add that it's continuous because of the basting lemma.
Because of what?
The basting lemma. Its continuity follows h.
Well, yeah, it's just because you can see that this is continuous and they agree at 1/2. Yeah.
This is the f of x and t and g of x and
Yeah, it's
final.
here.
hxt is equal to
X
final
what?
equation.
Yeah, x what? X comma 2.
F of
In the branch
Oh,
capital,
yeah,
it
it's
doesn't
okay,
have that.
yes, yeah,
Can we
it's,
take two inputs?
Yeah.
F of
Notation, just notation.
f
So
of
what?
t.
We just forget to put
Yes.
x.
Before
Oh,
everything,
yes.
yeah.
Thanks. Right. Is okay? So since it's a equivalence relation, we can define, for example, quotient, and so one of the notations which we might use is this bracket. And you might also see it somewhere else in the literature. Is by definition the set divided by this equivalence quotient with respect to this equivalence relation. Of course, I mean, in principle, this set can also be equated by using some topology as a set. So the set of continuous maps from x to y can be equated with topology. So this is, which I'm not going to go into. I mean, maybe you had this in your topology lectures. But in principle, this is also is defined not just as set, but as a topological space. But we are not going to essentially use this fact. Okay. So another important property about homotopy is the following. So let f and f prime be continuous maps from x and y. So from now on, earlier in the lectures, if I write map, I assume that it's continuous. If I don't mention explicitly otherwise, so all maps are assumed to be continuous. Will be two maps, two continuous maps from y to z, where x, y, z are topological spaces. And the statement is the following. So if f is homotopic to f prime and g is homotopic to g prime, so here, since I have map from x to y and from y to z, I can compose maps to obtain. I can compose continuous maps to obtain new continuous maps. So F composition of G and F gives me a continuous map from x to z, and the statement of this map is homotopic to G prime F prime. So in other words, the composition of maps respects homotopy equivalence. So let us show this. So again, suppose we have explicit, so we are given explicit homotopy F between F and N prime, and homotopy G between G and G prime. So we want to construct, present homotopy, let's say H, from the composition to composition of primed guys. We need homotopy H should be a function from x times interval to z, say that h respective to x times 0 is f composed with g, and h respective to x times 1 is f prime composed with g prime. And again, we can just explicitly write this function. So again, the small x will be element here, and small t will be element here. H of x and t is equal to, so use homotopies, given homotopies f and g. So we can just write g of f of x t.
Such that the F composed G F.
So you see, so let us see what happens when t equals 0. Is we get g of f of x 0, 0. So this is we know this is f, and we know that that when the second argument of g is explained by 0, we get g, right? So this is indeed composition of g and f. And the same thing for k equals 1. This is f prime. Of course, this is not the only, so the homotopy is not unique. This is just
Can we, in the first half interval, we form f to f dash, and in the second one,
yeah,
form
one
g to g?
could do this in this way. But this is so in this case we can simultaneously deform both an f and g, but we indeed could do as this.
Sorry, what's the other way? What's the other way?
Okay, let me write it. So the other example is let me erase this. So the other example is kind of similar to what we had for the composition. For when we show the equivalence relation, so we can take which t be equal. So we split the interval in two parts. That's from 0 and 1/2. And then we use here f of 2t x to t. And So here you see so first we can only we only deform f, the first function, and then we do the following g of f prime x. So again, you can understand this if you write this homotopy axis as follows from 0 to 1, to 1/2. So you can start with f g composition of f. So you can see that here in the beginning when t equals 0, this becomes f. So you get composition of g and f. Then we when we arrive at t equals 1/2, we get here f, big F of x and 1, which is f prime. So we get composition of g with f prime. And then we start, this is in agreement with the second line. So when t is 1/2 here, I get a big g when the second argument is 0, which is small g of f prime, which is indeed the same. And then we start deforming t from, increasing t from 1/2 to 1. And at the end, we have here big G of 1, which is G prime of F prime. So this is, let me call it H2. So this is H2. Any questions? So here is the advantage is that you can write it in one line. But here you have to write it. So in any case, so this is concludes the proof of the proposition that if you take composition respects homotopy equivalence. So in particular, this so one can make the following remark. This gives a well-defined map y so again, this was equivalence. This bracket denoted equivalence classes of continuous maps from x to y up to homotopy. So the map is given by we are taking some representative f here, some representative map here, and we map it to composition. And so we showed what we showed before. Essentially, it's not as well defined. The result doesn't depend on the choice of representative here.
I think the G circular. Here, G circular. The map.
Sorry, what?
This equivalent, this pair is mapped to the equivalence of class of F circle G. G circular.
Oh, okay, yes. Thanks.
So with this well-defined map, you mean magnification or continuous with this topology given by the equation?
Well, here I don't discuss topology even, but even the question is without any like asking question what is it continuous or not. It's just so if I say that the map is given by this,
Okay.
I have to show that. I have to show that it doesn't depend on the choice of representative. So because in the definition of the map, I choose the particular representatives
Yes.
in this quotient. So here I have to then I have to show that it doesn't depend on the choice of representative.
Okay.
So as I said, there will be a lot of definitions in the first lecture. Another definitions is that so a continuous map from X to Y is called homotopy equivalence if there exists continuous map from Y to X such that composition of G with F is homotopic to identity map on X, and composition of F of G with F is homotopy equivalence. Is homotopic to identity map on Y. So this gives you some map composition of F. So F is mapped from X to Y, G is mapped from Y to X, so this composition is a map from X to X. So I require that it should be homotopic to identity. And here I require that it should be homotopic to identity on Y. And so the first part so we also say that so the continuation of this is definition of homotopy equivalence. So X now to continue our definition, we say that X and Y are called said to be homotopy equivalent, or we may also say of the same have the same homotopy type, and the notation for this homotopy equivalence will be again using this one and tilde if there exist homotopy equivalence. So before we had, before this sign was there was an equivalence relation between functions. So we had two fixed spaces, and there was some equivalence relation, homotopy equivalence relation between functions of the space. Here we're considering a homotopy equivalence between the topological spaces themselves. So we can see, for example, if you have the notion of well, let me so let me make the following remark. So this is even not a proposition, if x and y are homomorphic, so it's a homomorphic topological spaces, then they automatically. So for homomorphism, I'm not sure what notation you used in topology lectures, but I'm going to use this kind of equality with the tilde. If they're homomorphic, then they are necessarily homotopic. Homotopic equivalent. So this is more or less obvious, because if they are, so let me write a proof of this remark. So if they are homomorphic, then by definition there exist G such that G continuous, there exists continuous. Again, by default everything is continuous. Y x and f and x y such that f g is identity y and g f is identity of x. So this is definition of homomorphism, right? But of course, if they are here, we just have they're identically equal to our identity maps. So of course, we can just choose here the constant homotopy. We just choose homotopy. Which is so we showed before that the homotopy is equivalence relation, so the function is homotopic to itself. So identity is homotopic. So this follows from the fact that this is equivalence relation. So we see that, so this is kind of the, if the space is homomorphic, they're necessarily homotopic, but as we will see, I mean, we will have an example later which will explicitly see that the inverse is of course not true.
But it is easy to find an comparison to the converse.
Yes. So, well, I will tell what in a few minutes. Well, but okay, I mean, just take. Well, let me. I'm not. Well, let me. Okay, the example which is easy to prove. I mean, just take a disk and point. The disk and the point are homotopic to each other, but not homomorphic. Okay. But let me.
Sorry,
I will show it slightly more specific.
the example is a disk whose what?
Point.
The disk is a point in a point.
The disk and the point.
Yes, they're homotopic, but they're homotopic equivalent, but not. Okay, from the definition, although we call this homotopy equivalence, we actually, from the definition itself, is not explicit. This is actually equivalence relation on the space. So we actually have to show again that this is the equivalence relation. So the statement will sound kind of tautological, but this is an on-trivial. So homotopy equivalence is equivalence from topological spaces. So again, we have to prove reflexivity, symmetry, and transitivity. First, we want to show that X is homotopy equivalence to itself. So again, we can just take F to be identity on X and G to be identity on X, right? So here X so the second, we want to prove that if X is homotopic to Y, as in definition, Y is homotopic to X. Well, this is obvious from definition. We just need to swap F and right. So the statement of homotopy equivalence was a statement that there exists F, the pair of F and G, such that the composition satisfies, well, this property. So the second is a bit less trivial, so we want to show the last one, the transitivity property, that X is homotopy equivalent to Y, Y is homotopy equivalent to Z, then we want to show that X is homotopy equivalent to Z.
We just compose the functions and use the well-definedness of composition.
Yep. So this was one reason why we needed one of the propositions before. So let me so we can kind of use short notation. So let F and G were maps as in definition of copatomic equivalence, so that such that F composition of F and G is homotopic to identity on Y, and composition of G and F is homotopic to identity on X. And similarly, for homotopic equivalent pair of Y and Z, we have, let's say, maps H and K, such that composition of H and K H is identity, homotopic to identity on Y, and composition of H and K is homotopic to identity.
Let's say that fact.
Okay, yes. Then, okay, so now we want to construct explicitly, so we want to show for a pair of X and Z, so we want to find a pair of functions which satisfy similar properties. So let me, I don't know, denote it by alpha and beta. So the claim is that I can take alpha to be a composition of H F H and beta to be G and K. I hope order is right. So at least this defines this is indeed the composition is sum up in correct between the correct spaces. Now we want to show that the composition of them in two different orders is homotopic to identity. First of all, let me start this composition of in beta. So this defines. So this is sum up from Z. So I need to show that this should be homotopic to identity on that. So this is HF composition G. Okay. Okay. So now I want to use. So since I can compose them in whatever order I want, I can use first this fact that the composition of F and G is homotopic to identity, and the property which I showed before that if in a composition we have a homotopic maps, so the composition is so if you have a composition of two functions and we can replace if you replace one function to a homotopic to another, the composition will be replaced by a homotopic function. So this is a homotopic to H identity Y. Okay. So then, since this identity, I can just get rid of it. I do composition of H and K, and I use this fact. This homotopic identity. So similarly, this composition will be homotopic to identity on X. This proof is it's completely simple. So this and the proof that the homotopy equivalence is indeed equivalence relation on topological spaces. In particular, in the diagram which I wrote in the very beginning of the lecture, this makes sense to divide, to consider a set of all topological spaces divided by homotopy equivalence. As indeed this is a weaker equivalence than homomorphism equivalence. So one can consider projection from the space of topological set of topological spaces model of homomorphism to set of topological spaces model homotopy equivalence. Any questions? So soon we will consider some examples, but before that I will still need to introduce some definitions. Another definition is the definition of retract of the topological space X onto a subspace inside X is a continuous function from x to a, such that if I restrict this continuous function R on subspace A, this will become identity of A.
So is it identity or homotopic to identity?
Here it's just identity.
Identical.
Yes, yes. So example, trivial example. So for any x, one can take A to be a point, as a subspace consisting of one point, where 0 is a point on x, and then take R to be a constant map. So all points of x are mapped to just one point. And of course, are restricted to A is identity. So R restricted to a point is just the point itself. Can I read this? This is a rather weak notion. What we will need actually is a stronger notion. The notion of, to be precise, it's a notion, so depending on where you look, if you look, for example, in the book of Hatcher, this is actually what is called weak deformation attack. What I will call it just information attack. And in many other places in the literature, people just define a deformation attack like this. And what is actually defined in the book of Hatcher as deformation attack is what in other places called strong deformation. In any case. So the definition which I'm going to use is a deformation attack of, again, topological space X onto subspace A in X the homotopy between identity map from X to X and R and retract R, which is the map from X to A, but I can understand this by, since I have a also inclusion map from A to X, a canonical inclusion map, I can consider R this as a whole composition as a map from X to X itself. Namely, we want a function, the function from X, so by definition of homotopy, function from X times interval to X, so that F restricted to X times 0 is identity on X and F restricted to X and 0 is R. But again, R can be understood as a map from X to X, so that its image each is contained in a subspace. the example. So let me have disk in R2. So let me run the example one. So disk realized in R2 is canonical way as a circle disk, for example, as a space of points. Is opposite value less than equal than 1. And I take say any point x0 inside this disk. This can be a center, but not necessary. Then, so this will be example of deformation. Retract of disk onto subspace of a disk consisting of a single point. Should be a homotopy as defined, so this should be marked from disk times interval to disk, where again I realize disk is a subspace of R2, and I will define it as x. T is x. So again, I can understand R2 as a linear space where I can add elements and multiply by real numbers. So you can see this is indeed a continuous function, which such that if t equals 0, I get an identity, so epoch xt is just equal to x, and if t equals 1, this is become a constant map to a point. So I can visualize this deformation effect again by drawing the trajectories of points, meaning that I fix some x and I vary and I change t from 0 to 1, and I draw the trajectories of such points, and they will look like this. This is what is called linear, usually called linear deformation. So this picture is a bit explains the name. So this kind of deformation, the retracted deform. Questions?
This is example of topic that knows on what space?
Yes, but I didn't show it here. I didn't prove it. But well, I can. Let me. I mean, in order to show that, you have to show that. Well, okay, no, but okay, it's easy to show here. It's clear that it's so. Well, let me show a bit later. I will show that the deformation retract is actually a homotopy equivalent between the space and the subspace. So once we show it, then from this it will follow that the disk is homotopy equivalent to a point, and but of course the disk is not homomorphic to a point because there is no one-to-one bijection. There is no inverse. When we write a bit more non-trivial example, so let X be another subspace 2 defined by this inequalities. So this is looks like an anomaly. And I'll take subspace A to be just a unit circle. X, okay, there. C, guard with the A. And then the deformation retract of X onto A can be realized as follows. So take F xt to be the whole so you can see that when t equals, again, when t equals 0, this becomes identity, and when t equals 1, you see that you map the image is a points per unit radius for unit. And again, you can realize it by drawing the projections. So one of the exercises is to provide an example of a more non-trivial, of a deformation of practice in a more non-trivial. The proposition is that if there is a deformation tract of X on A, then X and A are homotopically. The proof is the following. So we want so we have, so by definition of deformation retract, we have the following homotopy from 0 to 1 to X. So that at the beginning X is equal to identity, and at the end we have some retract R from X to A, which we can compose with embedding, which I will explicitly denote by IA, X, so that R restricted to A is the identity. In particular, so what does this mean? The statement can be just reformulated as follows. That so first of all, if the composition, so first this statement can be formulated as follows: the composition of IA is R is identity on A, right? So I compose embedding and then take a map from R map from X to A. This is the same as identity. This is basically formulation of the statement. And the fact that we have homotopy can be reformulated as follows. Identity, if we calculate the composition of R with IR, which is the composition of this with this, so it's the map from X to X. This is homotopic to identity on X, which is the statement. This homotopy is provided by A. So we can see that this is actually the definition of the homotopic equivalence. So there exist a pair of functions which satisfy this property.
Okay, so can you repeat this last part?
From here. So first of all, so this part is clear. So this was just a definition of. I reminded the definition of deformation of retract. Right? So there's a homotopy between two different functions from x to x. So one is identity on x, the other is the function r, which is can be understood as a map. So it can be understood as a first as a function from x to a, some subset, but it also can be understood as a function from x to x itself by composing this map with inclusion. So in particular, and so R is a retract. So by definition of retract, it's restriction. So if I can understand R, so in a way, so let me be more precise. So let me denote this map by R, and the composition actually by R tilde. So the homotopy is between identity and R tilde. So the statement, the statement that R tilde restricted not A is equal to identity on A. But I can also formulate it as follows. So if I compose.
But how we have here
this
we have a function from R from x to a, which is the retraction, retract mapping. We have a R from x to a, right?
Yes.
So this is a composition of function of x from x to x with the identity on a, which is the composition of IA with R tilde.
No, well, R here is well, retract is actually R tilde.
Oh, I see.
But again, since the statement that all the statement that the image of R tilde is in A, is inside A, and also the restriction of R tilde on A is identity. So the homotopy should be a function. So homotopy between a function from x on x. So at 0 we have identity. So the other side at 1 we have R tilde, which is a composition of R and inclusion. So the fact that the homotopy can be formulated as follows. So identity is homotopic to a composition of R with IA, which is indeed R tilde. So this is checked. So what about this statement? So this is a statement about composition of identity and R. Sorry, the composition of inclusion and R. So the composition of inclusion and R is a map from A to A, but from the fact that so we use the following fact that so this is when we restrict R tilde on A, this is the same as R on A, because we use the fact that the image of R tilde is the same as A. So this is what is written here is actually the composition of inclusion with R. So this follows from this.
Why here we don't have a tilde?
Because this is just identically.
Ah,
There is no, we don't need count. Is it clear? Or so once we have proven this, we can indeed show. So from this proof, it follows that the disk and a point are homotopic, and they are of course not homomorphic because there is no bijection. Another definition is the following: a pass in X is a continuous map from 0 to X. And, so the points F0 and F1 called endpoints. So this is start and this is end. So now we are interested in the following operations on pass. So of course you can visualize this section topological space X and realize path as some sort of trajectory. So this is f of 0. So this is the image of an interval. So the first operation which we want is taking inverse. So say f, let f be a path, then inverse f bar is a path. So is a path. Let me more precise. Let f be a path from x0 to x1. And then f bar, so inverse f bar is a path from x1 to here, so in the opposite direction, such that is explicitly defined okay, we have some path f. The inverse is essentially just a path going in opposite direction. So then composition. So let F and G be a pair of paths such that, so I want endpoint, so start point of G to coincide with endpoint of F. Then one can define a composition, which is denoted by a dot, F dot G. So this composition is a path, again a new path, which is explicitly can be defined by the following form. So when I change from S from 0 to 1/2, I take to S, and when S goes from 1/2 to 1, I take to S minus 1.
I think the condition doesn't meet because we want the end point of G to be the starting point of F.
No, I think it's the endpoint. So for example, when S is equal 1/2, here we have F of 1, and here we have G of 0.
So we.
So it's
okay.
it goes like this. So we start with F, and then
Sorry. Okay.
and then G. So this is the composition. So this operation has so before we define homotopy between just arbitrary functions, but we want to define what is the homotopy between paths F and prime. The definition is almost the same as between just maps, but with additional condition. So the beginning of the definition is the same. So it's a map from X to an interval to X, such that when I restrict it to 0, it's F. When I restrict it to 1, here means the value of the second argument. Get F prime, but the additional condition is that so here when I consider paths, I want to consider paths they have the same start and endpoints. So let me put in x0 and x1. And I want the same conditions that for homotopy. So here I want this is a map. This homotopy between maps from 0 to x. So let me be more explicit. So I write. So let me denote this variable by s and this variable by t. So this will be variable corresponding to a path variable, and this will be corresponding to homotopy. And so this part looks like the ordinary homotopy, but I want to have a condition that so for any t, if s is 0, I want to stay at x0, and for any t when s is 1, I want to stay at x1. Essentially, what we when we consider a homotopy with the n of a prime, looks like before, but we keep starting points to be fixed. And so this the proposition, which I'm not going to prove because the proof is completely similar to what we had before, is this is so we call this so f exists, then we call again two paths to be homotopy equivalent in terms of this path homotopy. But I will use the same notations, and this is defines equivalence. Is equivalence relation on the space of paths.
But isn't here there is some abuse of notation, because if we have two buses, we can consider them as a map
Yes.
of.
Yes, there is abuse of.
But I mean, it could
So
be
we have to say that here we just don't consider this as a maps, but as a paths, where paths can be understood as a maps equipped with additional data, additional input, as a start and end points. But indeed, it's a bit of. So we have to be clear.
But if there is a homotopy as mapped, does this imply that there is?
Not necessarily. But the other way, of course, implies. This is a particular type of homotopy. This is more restrictive homotopy. So I have to finish soon, but let me just maybe formulate the proposition which I will need. So again, I maybe won't prove it. I will leave some of the points to prove to yourself, but because this will use very similar techniques to what we had before. But so let me. Anyway, let me first formulate the statement. So f is as a path, f and f prime are homotopic as paths. Then the inverse path is homotopic. They are homotopic between themselves. Then b is if f is homotopic to f prime, g is homotopic to g prime. So I can formulate this as the properties of paths from the composition of f and g is homotopic to composition of f and g prime. C, if I take the composition first of f and g, and then this h, this is homotopic to composition done in a different order. And finally, if I take composition of f bar, this is homotopic to constant path. The constant path is just path which stays at one point. This identity map. The path with the same end and start, and which is just constant. So I think, so I have, it's 5:30, I think I still have to finish.